All right, we're going to talk about our last functions. Lily? Yes? You ready?
Yeah.
Okay, I know you're a little distraught right now, but...
I'm sorry, Lily.
We're going to talk about the second to last type of function that we're going to deal with in this class, which are called exponential functions. And there's a lot of buildup to this before I can actually show you what they look like. So let's take care of a few preliminary things. Remember from some class before this what are called the law of exponents. We will use all of these laws in some way, shape, or form as we're working with exponential functions. So laws of exponents, things like this. I'm going to use the same letters and notation that the book does. If you have something raised to a power times the same thing raised to a different power, what can you do to combine those together? You add the powers. So this is a to the s plus t. All right, so if you have the same base, we call that the base. We call the s and the t the exponents. Then if you have the same base, different exponents, you multiplying those together, you add the exponents. That's different than this, which would be a base raised to a power and then raised again to a power. In that case, you multiply the two exponents, the s and the t together. So a to the s times t. So all of these laws that I'm giving you are things that you've probably worked with in the past. It's just maybe been a while. Another property or another law, those are two of them. If you have two different bases being multiplied, and you decide to raise these to a power, what can you do with that power to remove the parentheses? You can apply the power to both the a and the b separately. So it's almost like distribution, although we don't call it distribution. The power, the s power goes to the a and then to the b, as long as this operation between these two was multiplication. Another property. If you have something raised to a negative number, it's the same as dropping it down to a denominator and changing the power to a positive number. Do you remember that? Something raised to a negative, it drops down. What if you have something that's negative on the bottom already? Like something raised to a negative power on the bottom. You can bring it up, right? So this property could also be written this way. If you have 1 over a to the negative s, this is just a to the s. So if you already have a fraction and you have something to a negative power, you can bring that up, and then it just becomes a to the s. All right, two more. What is 1 raised to any power? 1. What is 0 raised to any power? 0? No, it does. It exists. 0 raised to any power would be 0 to, like 0 times itself times itself. So this should be 0, but with one exception. Hold on. As long as the s is not 0. 0 to the 0 causes a pretty big problem. Well, because let me write the next one down here. What's anything raised to the 0?
0.
Nope.
Wait,
1. Okay. So look at 1 raised to any power is 1 times 1 however many times, and that's just going to give you 1. 0 raised to any powers is 0 times 0 however many times, it's just going to give you 0. But when you do, and then if you do a to the 0, it's 1. Now why is that? I mean, a lot of people have trouble with this. What does this mean? So maybe I can help convince you of this, all right? I may or may not be able to. Let's see if I can. I'm going to make a little table here. What's 4 cubed? It's 4 times 4 times 4. That's
16 times 4.
64? Okay. What's 4 squared? 4 times 4, that's 16. What's 4 to the first power? Just 4. Okay, so what's happening each time? If I want to go from 64 down to 16, what do I do? Divide by 4? From 16 down to 4, divide by 4, right? And if I do 4 to the 0, then I should get whatever I get when I take that and divide by 4, which should be 1, right? And then what's 4 to the negative 1? Well, according to what I've been doing, it should be whatever I get when I take that and divide by what? 4? Divide by 4? 1 divided by 4 is 1/4. Are these two the same?
Yes.
Yes. 4 to the negative 1 is 1 over 4 to the positive 1. That's using one of the properties I just put up on the board. A to the negative s is equal to 1 over a to the positive s. So this matches what this is, right? So do you see that pattern? If you agree with that pattern, then it makes sense that any number to the 0 is 1. If you agree with that pattern. All right? Is that enough? Can I move on? Did I sell you on that? All right. Except for 0. Here, a couldn't be 0. And so 0 raised to the 0 is undefined. Just as an FYI, all right? I think you've all heard before you can never take a number and divide by 0, right? You can't do that? That's undefined? Well, you can't take 0 and raise it to the 0 either. That's undefined also. Both of these are undefined. All right, that's it for the properties, the laws of exponents. Let's now just, if you have your calculator, get your calculator out. If you don't, you need to bring it next time, okay? Everyone got that? Bring your calculators from here on out every single day. Not your phone calculator, your calculator. The one that you'll be using on a test. I have no restrictions as to what calculator you can use.
I was going to ask you, do you prefer scientific? Or
It has to be scientific. It has to be able to, well, how can you tell if your calculator is scientific?
It says scientific on the box. It graphs.
If it has a bunch of keys that you don't know what they are, then that's a scientific calculator. That's pretty much it.
But then therefore, like in the next math classes, we are going to need a graphing calculator.
You never need a graphing calculator.
And that sucks.
Okay, you never need one, but having one is a good thing. Okay, but it's not required to do well. But it's a good tool if you learn how to use it. All right, like the TI-89, that is more powerful than you even understand right now.
Oh no, it factors.
I know it factors. It does a lot more than that too.
It
Yeah.
does like addition and
It does calculus, which is
Yeah. It
All right.
like even has like a little subsets of like trigonometry and calculus and stuff like that.
And there's another one that's even not, it's the same brains, but it's the Nspire, it's color graphing. Anyway, all right, we won't get into that. All right, so please with your calculator, I'd like for you to do the following, all right? See if we can practice doing these examples. Find on your calculator what 2 cubed is. Now I know you can all do that in your head.
it's 39, right?
That is right, it's 23 actually. It's just 2, 3, 23. So just make sure you can do that. Make sure you can do that, okay? Type it into your calculator. I want you to try it and make sure you can get it. Yes? 2 to the 3rd power. Because everybody's calculator is going to be different, okay? Depending, like Jordan's calculator, you probably have a little key there that says like x to the y, or maybe it says y to the x.
Yes.
That's your raised key. But other people, their calculators have that key, which is called the caret key, and that's what we use to raise. And so it all depends. So we need to work this all out now, all right? Everybody get 8? Yes. Okay, so we're going to move on. Now what I'd like for you to do is -2 to the 4th. What do you get? 16? You should be getting negative 16. Because I didn't ask you to do this. That's different. Right? So you need to be able to type this correctly on your calculator. This should get you negative 16. This should get you positive 16. So use your parentheses. On this one, you don't use parentheses. And if your calculator is spitting out 16 instead of negative 16, then we/you need to figure out how to type it in properly. All right? So if any of these you're not getting on your calculator, put a little star next to it, and then maybe if we have some time at the end of class or something, I can address that with you. All right? Let's try something a little harder. Let's try 1/4 to the negative 2. And you should be getting here, anybody? You should get 16. Try this one. Pi is a number, isn't it? And you should have a key on your calculator for pi somewhere. I'd like for you to take pi and raise it to the pi and see what you get. 36 point something? Okay, so when you get a decimal like that, we will put approximately equal to 36.4. Let's go 3 decimal places for now. So these squiggly equals means approximately. All right, let's try everyone knows that that symbol pi stands for a number, right?
Yes.
3.14, something like that. There's this other number called e, and there's also a key on your calculator for that. And I want you to do e squared and tell me what it is approximately. Now this is where we start to run into some issues because of the way these calculators work. So see if you can find the key and get 7.389 approximately. We'll just go 3 decimal places for now. Because everyone is going to have a different, like someone's calculator is only going to go out 6, some's going to go out 10, some's going to go out 14. It just depends on your settings on your calculator. Okay, so remember, put a little star next to these if you're having trouble doing it, or ask your neighbor. On your calculator, you have to actually, because of the way your calculator works, and I think, Jordan, yours is probably the same way, you have to type in 2 first, and then you have to type in the E. But I can help you resolve that at the end.
I mean, I have my other calculator.
Okay, you have another one? Bring that other one then. Okay. Don't drive yourself crazy with that one. All right, so basically what I'm telling you here is that you should be comfortable with your calculator to take basically any number and raise it to any power. All right? Now, let's talk about exponential functions.
Yeah.
An exponential function is a function of this form. And I'm about to write out what it is. F of x equals something. And I wanted to show you something first before I did this. So let me show you something that's a little more exciting than me just telling you what an exponential function is. Who has a piece of paper they would like to sacrifice? Yes? There you go. Thank you, Giovanna. All right, everyone. This is just going to be a little demonstration. We're going to take this piece of paper and we're going to create a table. We're going to count some things, all right? We'll get back to what an exponential function looks like in a second. In this table, I'm going to have the number of folds I have in the paper listed here, and then here the number of rectangles that you see. So right now I have no folds in the paper, right? There are no folds. How many rectangles do you see? One? Okay. If I fold it one time, right, and I don't know, I can't, it's hard for me to mark that edge, but you can kind of see if I fold it one time and open it, I've created two rectangles, right, along the fold. So fold it one time, and now I have two rectangles. So I'm going to fold it back, and I'm going to fold it a second time now. How many rectangles am I going to have when I open this up? 4? So let's see, I open it up. 4 rectangles. So 2 folds, 4 rectangles. 1, 2, now 3 folds. What do you think? 8? Just one person? 8? That's it? 8, 16. Anyone say 6? No? Think it's going to be 8? You think it's doubling each time? So when we open it up, we have 4 along here, 4 along here, so that's 8. So 3 folds, we get 8. Right? Let's try one more. One more fold. 16. So if I open this up, try to open it up, I'm getting 16. 4 across top, 4 down the side. So there are 16 rectangles. And I could keep doing this, right? But there's actually a physical limit to how many times you can fold a piece of paper. Anybody watch Mythbusters? Yep. Yeah. That's an old episode, right? They were trying to test the theory of how many times you could fold a piece of paper. So they took this piece of paper, it was like in an airplane hangar, right? It was like the size of a football field or something. It was bigger, and they took it and they folded it, and they got a steamroller, right? Like a big old steamroller, and that's what they used to like make the creases. And I think the max was 13, 17, I don't remember. Try it for yourself, not here, but take a piece of paper, see how many times you can fold it. And then you'll find that you get to a point where you can't fold it anymore. Physically, it's impossible. I'm sorry?
It's only 8 if you're a human.
I think I've gone past 8.
I don't think you have.
Ooh, okay. I took a piece of paper out of a Bible, which is really thin,
Okay, 5.
right? No, like the little blank paper in the back where you can write a note. I just took that out and I folded it over and folded it over. I think a human can get past 8, but I don't know. We won't test it right now. Here's my question to you. How many, if I can't get past 8, then since I can't test it, how many would I have if I did 9 folds? How many rectangles, if I could do it, how many would I have?
Is there a function for that you can give us?
Well, see, that's what I'm trying to get at here. I think you could get it by just saying, okay, at 5 folds it's 32, at 6 folds it's 64, right? And you can keep doing this until you get to 9. But that means in order to tell me what's happening at 9, you actually have to figure out what's happening at 5, 6, 7, and 8. And if I change that to like 90, then you'd have to go 5, 6, 7, 8, all the way down to 90. That's going to take you a while. So is there a function, okay, is there a function that will actually do this? That will take 0 over to 1, that will take 1 over to 2, that'll take 2 over to 4, and so on and so forth. A function that I can define. You plug in 0, it spits out 1. You plug in 1, it spits out 2. You plug in 2, it spits out 4. You plug in 3, it spits out 8. Anyone see what it is? I'll give you a hint. It has an X in it, yes. Exponential functions. Why do you think exponential functions are called exponential functions? You have exponents, right? Well, so did x squared. X squared had an exponent. But with this, where's the variable? And here the variable's in the base, isn't it? And the exponent was 2, and that never changed. So with like a parabola, a polynomial, the x was always in the bottom. Exponential functions, where do you think the x is going to be? In the exponent. That's going to be the thing that changes, and the base is going to be the thing that doesn't change. So let's take a look back over here. Do you agree that 2 is 2 to the first power? Do you agree that 4 is 2 squared? Do you agree that 8 is 2 cubed? And that 16 is 2 to the fourth? In fact, 1 up here would be 2 to the what? 0. And do you see the connection here? Do you see that the input, the thing that I'm plugging in, is always the thing that's the power? The 1 here is just the power on 2. The 2 here is just the power on 2. The 3 is the power, right? So if I define this function for this to be f of x equals what? 2 to the x, then that should model what's happening with that folding stuff. So fold it 9 times for me. Get your calculator out and plug 9 in there, 2 to the 9th power, and tell me how many rectangles we would have. What is it? 512. How about for 5? I want to list a couple more of these out because I'm about to talk about something random. Let's see. For 5, I'm going to continue this table over here. What was it for 5?
32,
And for 6?
64,
And for 7?
128,
For 8?
256,
And for 9?
512.
512. Anybody recognize these numbers? Like 2, 4, 8, 16, especially these, like 16, 32, 64. They're, well, no, because 32 is not a perfect square. Think about the real world, okay? Think about your phone. What are they always, when you buy a phone, they're always like it's always like 32 gig, right? Like when you buy an iPhone, they don't give you an option for a 24 gig iPhone, right? It's always like what? I don't know what they're at now, but 8, 16, 32, right? 64.
Yeah.
Why not 60? Why not 57, right? Right? Why not? What does that have to do with any? Are there any computer science majors in here? Okay, so any idea?
It has to do with how many times we can fold the iPhone in half.
That's yes. No, this is very fundamental. Any idea? No? You're so quiet over there always, but no? Okay, what does a computer know? What's the only thing a computer knows? Ones and zeros, right? On or off? We call that binary. We call that binary meaning 2. There's only two things a computer knows. You either have an electrical signal or you do not. And we represent that with a 0 or a 1. That's it. So everything is what we call base 2. So in computers, everything is basically in powers of 2. So when you go for memory, they make everything in powers of 2, then it's got to hit at one of these numbers. That's where it comes from. Random, almost useless information, but it's just good, you just know now, all right? They're not just like, it's because the language of a computer is binary that you always have those types of memories. Okay. All right, so that was the folding paper there. Let's now get back to what the exponential function looks like. So I'm continuing with what I just erased. F of x equals c a to the x. I think that's what's, and that's multiplication. All exponential functions look like this. C, where c is a number. A, which is a number also. But we have some restrictions on the A. C can be any number, all right? A can't be 0. In fact, A can't be negative. A has got to be positive. That means A can't be 0 or a negative number. And also, A cannot be 1. Because if I plug 1 in here, what's going to happen? 1 to any power will just be 1. So it's just going to be a flat function. It's not going to do anything. So we just kind of throw that out so it's not, doesn't look ridiculous. Also, there is a restriction on C because it would be stupid to to let c be 0, right? Because if c was 0, what would happen? It would just be 0. The whole thing would be 0, and it wouldn't make it, you know.
Can we just say that a is greater than 1?
No, because a could be a fraction like 1/2. Okay. Because when you raise things to when you raise negative numbers to powers, weird things happen. Think about like what's -1 to the first power? Well, that's 1, right? But what's -1 squared? Well, that's -1, right? What's -1 to the 1/2? Well, that's the square root of -1, and that's an imaginary number. So things start getting really, really weird. And so we say, look, if we're going to talk about what are we calling exponential functions, we are never going to allow our base to be negative because it just gets, it no longer falls into that category anymore. Okay, so anytime we see something like this, we have an exponential function. An example of an exponential function is the one I just gave you with the folding paper, right? The folding paper, the function we came up with
2x.
was f of x was 2x. 2 to the x. 2 raised to the x. Yep. What would c be for this one? What's c here? 1. It's the number that would be multiplied out in front of everything, which is 1. And a for us here is what? 2. The a is a very important number in the problem because it's going to actually dictate how the function behaves. I mean, it's the most important number, so we have a special name for it. It's called the base of the exponential function. Right? So this a right here, put over here the base of the exponential function. So let's look at a graph of one of these, all right? Specifically, let's go back to the folding paper one and look at its graph. That function, 2 to the x, is going to look kind of interesting. So let's graph f of x equals 2 raised to the x. Now remember, we have covered lines, parabolas, polynomials, and rational functions up to this point, right? We know how to graph those. And lines were easy, parabolas a little bit of work, polynomials a little more work, rational functions a lot of work. Exponential functions are going to actually require the least amount of work, right? Which is good. Well, lines are easier than this, though. And the way we're going to do it is this. We're going to go back like we're back in grade school almost. And we're going to make what we call the t-table. The good old days. What we're going to do is just plot some points. So let's start with some numbers that are easy to plug in, like let's do 0, 1, 2, and 3. So what would happen if you plug 0 in here?
1.
You get 1, 1 you get 2, 2 you get 4, and then 8, right? So let's try and graph that on an x, y axis here. So at 0 for x, I get 1 for y. So that's a point. So this is a point, 0, 1. Next one's 1, 2. Next one's 2, 4. Next one's 3, 8, right? My next point, I go out to the right 1, I go up 2. The next one, go out to the right 2, I'm up at 4. Then I go to the right 3, and I'm up at 8, which is up here. And then where was I at 9? 512. I mean, that's just way up there, isn't it, at 9? At 4, I was what, at 64? No. What was that? At 4. 16, and then 32, and then 64. It's taken off, isn't it? It's taken off. It's almost like a parabola. Do you agree? Kind of looks like a parabola. But let's take a look at the other side of the graph. We're just going to connect those with a nice smooth curve. What's happening over here? Is it going to turn back and look like a parabola on this side? No. So let me try it. -1. So you plug in -1, right? 2 to the -1. Using the property of exponents, that's 1 over 2 to the first power, dropping it down, which is just 1/2, isn't it? So that means that at -1, I'm at 1/2, which puts me here. How about at -2? 1/4. 2 to the -2 would be 1 over 2 squared, which is 1/4. So it's even closer to 0, isn't it? The next one would be 2 to the -3, which would be 0.125. So that's 1/8. I'll let you check it yourself. This is 1/8 though. I'll write it. 2 to the -3 is 1 over 2 to the +3, which is 1 over 8. Isn't it just all of these numbers but 1 over it? Yes? Okay. So as I move out to the left, I'm getting closer and closer to 0, aren't I? Am I ever going to get there? No, I'm never going to get there. So what did we call it when we had this thing that pulled our function towards it? Horizontal asymptote. I actually have a horizontal asymptote over here. This right there, that's a horizontal asymptote. Does that horizontal asymptote go on this side though? No, it doesn't. So it looks like for an exponential function, we will have a horizontal asymptote, but it'll only be on one of the sides of the function, not on both sides. This side is taking off, headed up towards infinity, right? It's headed to infinity and beyond. And then back here, it's headed towards 0. With me? Yeah. All right. So this does not look like x squared, right? Does not look like a parabola. If we were to draw x squared on here, right? You plug in 0, you get 0. You plug in 1, you get 1. You plug in 2, you get 4, right? Where would you be here at 3? 9 would be higher than this one, wouldn't it? So you might get the idea that, you know what, this parabola is actually growing faster than the exponential function, but it's not even close. Go out to 9. If you plug 9 in here, where are you? 81, but where did we say we were at 9 on this? 500 something. So the growth of the exponential function here is so much faster than the x squared function. You'll see the difference between the two? 2 to the x versus x to the 2. So that's why when you watch the news and they're talking about, you know, the crime rate is growing exponentially, they always use that word exponentially. That's to somehow get the idea of very fast growth, right, across to people, right? That's the way you understand it? It's not being used properly. I mean, when you say exponential growth, you're talking about a specific type of growth. I think they should just say it's really fast or something instead of this. Okay, that's what 2 to the x looks like. How would we do a different exponential like 4 to the x? What would be the only difference here? These numbers, right? So you would go 0 would get you what? 1 still, right? 1, though, would get you 4. 2 would get you 16. 3 would get you 64. And so you keep going, right? And when you graph it, you're still going to get this general shape, but it's just your points are going to be at different places. So at 1, you'll be up here at 4. At 2, you'll be, what, at 16. So it would actually grow even faster than this one, wouldn't it? Understand? So let's write something down here just to kind of summarize what we've done so far. The graph of f of x equals a to the x, where a is bigger than 1, looks like this. Guaranteed, if you give me an exponential function and you tell me that that number right there is bigger than 1, so it's like 2 or 4 or 5, or you could even have something like pi be down there. As long as that number is bigger than 1, then your graph should always go through this point, 0, 1. Why? Because anything to the 0 is 1, right? So that point will be there. The right side will go up, right? The left side will go down towards a horizontal asymptote. Now, how fast it grows, right? The steepness of this is dependent upon how big A is. The bigger A is, the faster it grows, all right? So, what's the domain of this? Look at your picture. Your domain, all real numbers. Negative infinity to infinity. What's the range of this? 0 to infinity, and you said parenthesis, right? Because we will never actually be 0, right? You can never, your function will never hit 0? Okay. Where is it increasing? Always, right? This is always increasing, isn't it? So we say negative infinity to infinity. Right, when you have an exponential function where your a is bigger than 1, your graph will always go up from left to right. That means it's increasing. And so it's happening everywhere. Where is it decreasing? Never, right? How do I say that? How do I say it doesn't decrease as an interval notation? What do we use in there? Do y'all remember this? Do you remember that? The empty set? I think we did, because I mentioned that in the military they use that for 0 a lot of times. No? Really? Okay, well, well, I don't trust you, David, but I trust some other people in here. If they say I didn't do it, I didn't do it. I wouldn't trust David. He's into like witch magic and stuff. He's been doing some stuff, right? Don't act like you don't know now. He's like gets me after class and does tricks and okay. Oh, the empty set. Card tricks, and he's the devil. Yeah, basically is what.
You got me.
Okay, so this is what happens if a is bigger than 1, right? What happens if a is less than 1 but still positive? We have to figure out, like we haven't seen that happen yet, have we? So I'm going to look at one of those. But this is the general idea. Let me make sure that I covered everything here. Increasing, it has the point 0, 1. It's continuous, meaning it's nice and smooth. There's no gaps, no jumps, no corners, right? Nice, smooth curve. Domain we've got. Does it have a y-intercept? Yes. Does it have an x-intercept? No. Okay. All right. Let's now look at, I'm going to give you a different example. And to do this, I'm going to use that sacrificial piece of paper. But I'm going to do a different problem. It's not going to be folding the paper. Let's say that we have this piece of paper, and let's say the piece of paper here is 1 unit wide. Okay, so the width of this paper is 1 unit. Ooh, that looks terrible. 1 unit. Yeah, but I want it to be 1 unit. So like imagine it's like 1 foot, 1 meter, whatever, all right? Okay, so I'm going to make a table, and I'm going to put cuts, and then here length. So right now, I have not made any cuts on this paper, right? How long is it? 1 unit. So no cuts, 1 unit. Now what I'm going to do is I'm going to take my scissors, I'm going to cut it right up the middle. Cut it in half. I'm sure David could do this. Just put it behind your back. It would be cut in half, but I'll do it with my fingers, all right? So how long is it now? I cut half and it threw half away. So 1 cut, it's half, right? Half a unit? Okay, I'm going to cut this a second time. How long is that? It's a fourth, right? Because look, I did half of a half. Half of a half is a fourth. 2 cuts, 1/4. Do it again. 1/8, right? 3 cuts, 1/8. Do it again. 1/16. Now theoretically, I could keep doing this, right? When I say theoretically, I mean if we take like physical limitations out of this, if I had a perfect knife, I could keep cutting this in half forever. If we don't get into a debate about, okay, you get down to the quarks or anything like that, just completely theoretical. A perfect knife and a piece of paper that never runs out of paper, like it, you don't get to an atomic one like cell or anything. You know what I'm saying? Just, all right, you got it. Theoretically, this keeps going, right? Okay. What's the function that gives us this? This is 1/2. This is 1/2 squared, isn't it? This is 1/2 cubed, because didn't we say we're taking half of a half and then half of a half and then half of a half? So we keep on doing half each time, so we keep on doing multiplying by another half every single time. And so it looks like we could come up here and rewrite 1 as being 1/2 to the 0. And that's going to be a 1, and that's great. So the function appears to be 1/2 to the x. We all good with that?
Could you also do 1 over 2 to the x?
1/2 to the x. Yes, this could also be written as 1/2 to the x, which could also be written 2 to the negative x. But we're going to look at this for right now, okay? Just this. This is going to wind up. Do you remember when we talked about translations of functions, moving them up, down, left, right, reflecting them over the x-axis? When you put a negative, or sorry, I said x-axis, y-axis. When you put a negative in front of the x, it's a reflection over the y-axis. So you'll see. We're a little ahead of ourselves here. All right, so if we were to graph this, okay, if I were to come in here and do a pretty decent graph of this function, then at 0, I'm at 1. So that follows kind of what the other one did, right? 0, 1. But when I go to 1, instead of it going up, it's doing what? It's going to the 1/2. And when I go to 2, it goes to 1/4. And then it keeps doing that. Does this ever get to 0? No, it doesn't, right? So this is getting closer and closer to the x-axis this way, right? But negative, which if we start talking negative, then we can't talk about the cuts anymore because it doesn't make sense to have a negative cut, all right? But just purely in terms of the function itself, if I plug negative numbers in here, let me just do one of them. If I plug -1 in, okay, to the function, I get 1/2 to the -1. And when you raise a fraction to a negative number, what can you do? Flip it. Now that's a property of exponents, but the book doesn't list that as a property of exponents. I don't know why. If you have a fraction to a negative number, you can flip it. Yeah, I'll put it over here. If you have a fraction, x over y, raised to a negative power, that's the same as y over x to a positive power. So flip the fraction over, make it positive exponent instead. So that means at -1, I'm at 2. And at -2, you'd be at 4. What does this look like? Doesn't that look like 2 to the x, doesn't it?
Yes.
But it's flipped over, right? It's, and that's, you can see here that that verifies it. But so this is the graph of f of x equals 1/2 raised to the x. When you compare that to 2 to the x, which is the one we did before, that looked like, oh, I missed it. The one that looked like this, they're very similar, except they're just mirror images, aren't they? Just take that and just flip it. All right? So we do not call this, see, you could have someone talking about exponential growth, or saying it's growing exponentially. This is exponential, but it's not growth, is it? I mean, we call this exponential, anyone know?
Decay.
Decay. We call this exponential decay. So let me now summarize this. If you have f of x equals a to the x, and 0 is less than a is less than 1. So the base, all right, is not bigger than 1 now. It's between 0 and 1, like 1/2 was, right? 1/2 is between 0 and 1. Then your graph is going to look different. Will it still go through 0, 1? Yes. It'll still go through this very important point, 0, 1. Except that on the left side it'll go up, on the right side it'll go down. What's the domain? Same thing that the other one was. What's the range? Same thing. What's the... It's not increasing, it's actually decreasing all the time, right? It's still smooth, still has a y-intercept, still doesn't have an x-intercept, right? So there's a lot of similarities between this and when a is bigger than 1, except that we have decreasing instead of increasing. Understand? So we call this decay. On the other graph, just go on the other graph and put growth on there. Okay, the other graph was exponential growth. This is exponential decay. Now, I mean, what we really want is we want functions. The reason that we like to work with functions in science classes and just application physics, the real world, because we want to take a situation in the real world and we like to try and find a function that models what's going on, so that we can try and predict behavior later. And one of the things that we use exponential decay for is something called radioactive decay or half-lives. And we'll talk more about this. We'll get into applications. Hopefully we'll be able to get into the applications. But what is a half-life? Anyone know what a half-life is?
It's a pretty sweet game.
It's a game, right? It's a video game.
Yeah. How long to active? HalfLife 3, right?
I've never played it, but I hear it's pretty popular.
Still waiting on HalfLife 3.
So you have different elements on Earth that, like if we have it, here it is, and they decay naturally. Okay, they start, almost think of it as like a fire. You have a big old bonfire, it's burning hot. You come back an hour later, it's dwindled down. You come back the next day, you still have some heat in there, deep in there. You got the ambers in there, right? Ambers? Embers. Right? And so it's still warm. So it's starting to go and get cooler and cooler and cooler, right? Same kind of idea. And so depending on what the element is, we call the half-life the amount of time required for half of the, yeah, you could, well, it depends on, how technical you want to get here, right? Okay, we can say half of the stuff, no matter what it is. All right, so we're not getting very technical.
Real scientific.
Yes, thank you, thank you. Half of the stuff to decay, to go away. That's the general idea. You got some stuff, it's going to start decaying. How much time does it take for that to decay, right? It might take 1 day for that to happen. In that case, your half-life would be 1 day. Then another day, you have this much. And then another day, you have this much. Another day, you have this much. Another day, this much. Another. Is it ever really going to ever really be gone completely? No, not necessarily. Again, this gets theoretical, but you're always going to have a little bit of stuff there, right? And maybe it doesn't matter. You get to a point where it doesn't really matter anymore, right? Now, it might take a day, it might take a week, it might take 1 second. It just depends on what the stuff is, all right? And it could take thousands of years, it could take millions of years, or billions of years. So, have you heard about carbon-14 dating?
Yes.
Carbon-14 dating, they find the carbon-14 in human bones, and, once your body maintains a certain level of it, but once you actually die, it starts to decay. And they know that rate of decay. They know the half-life of carbon-14, so they're able to determine from measuring the amount of carbon-14 in your bones how long you've been dead. Okay, that's the way carbon-14 dating works. And we'll do some work problems later with carbon-14. We'll figure out how old a bone is or something like that. But the whole reason I'm getting to this, okay, is to bring up something that happened back, I believe, in the 80s in Russia, Chernobyl. Y'all remember Chernobyl? How many of you, show of hands, how many of you know when I say Chernobyl what I'm talking about?
Yeah, I was there.
Okay, so you were there? That explains a lot. That explains a whole lot. Radioactive material does major damage to people.
I really made that too easy for you.
Yes, you set me up, thank you.
I orchestrated it.
So what was Chernobyl? What happened?
Nuclear meltdown.
Nuclear meltdown in a nuclear plant, right, where they were creating energy. They lost control of the nuclear reaction, and the core of the reactor melted down. Got to just huge, just unbelievably hot inside that core, to the point at which basically it was like the core was like a piece of butter, and inside was this, hot knife. Just the core of it just melted, started melting through the bottom. There was an explosion, but it started melting through. And to this day, nobody lives in Chernobyl. Now, why is it that no one lives in Chernobyl? It's too radioactive. Because the material that was there is still there. What are you doing? Okay, I thought you were texting. No? Okay. So it's still there. Still, if you go to Chernobyl, they say unsafe levels of radiation, you'll be dead within a certain amount of time. Anybody know how much bad stuff was there that day?
Not very much.
That's a good answer. Yeah, not very much. How much? Any idea? Anyone want to guess? We're talking about this city that's been uninhabited since the 1980s. I believe it happened in the 80s. And because of this nuclear material that still is like glowing, Anyone have just a guess?
Are you looking for
7.
Like how much of the radioactive material
Like a pound?
did they lose?
7.
Was it 7 what?
Grams.
Oh, the reactor was, I think it was
Miles.
42 megawatts. I think
It was 10 pounds. It was 10 pounds.
Wait, what?
It was 10 pounds.
So 10 months of birth.
They basically like, a backpack worth of stuff that still has caused this city to be uninhabited. 10 pounds, that's it. And the half-life for it, I don't want to guess, I don't want to act like I know it, I don't remember it, but it's like hundreds of thousands of years, I believe, is the half-life. So like, even though that happened in the 80s and it was 10 pounds, there's still like 9-point-something pounds of it there. Like it's decayed, but just not very fast. That's why there's no like real plan to go back and, recover it. I think they sent some firefighters in when it first happened, and the core had melted down, and they sent some people in, firefighters, and they just like poured concrete, and they tried to encase it. And a lot of those firefighters died. I mean, they kind of knew that when they went. They kind of knew they were going to not make it.
Same thing happened on K-19. They did that with the whole, with their reactor that happened on board.
Uh-huh.
That movie.
Yep.
They went to
Yeah.
the reactor farm and it was at power, so there was still a lot of radiation going on. So
Mhm.
they had to take and all that.
Someone had to take care of it. Yeah.
Had to be buried in less than 5 miles. It's crazy stuff, man.
Yep. So I'm trying to connect this to, look, in the real world, we do like to model things like radioactive decay with exponential functions because they do a great job of modeling that decay without it actually ever going away, right? All right, we got to keep moving. So how about we try and graph some other exponential functions? But I'm going to start to make this a little more complicated, all right? All right, here we go. So let's sketch f of x equals e to the x. Now, I told you this number e was a very special number, right? It's like pi. This particular function is called the natural exponential function. E is approximately 2.718. Just like remember pi, everyone knows, well, pi is about what, 3.14? Well, E is a very special number in mathematics, and it is about 2.718. And I think at this point, it's kind of difficult to explain to you why this number is so important, like why that comes up, why we call it the natural exponential function. You have to get into Cal 1 to actually see why it's a good number, why it's an important number. But I'll try and explain it to you in a very, very layman's terms, I guess. We were looking for a function that behaved a certain way. And we were looking and looking and looking, and we finally found it. And this is the function that behaves the way that we need it to behave. That's about it. I mean, we looked for it, and it turned out that this was the one we were looking for, and it's the only one that behaves that way. No other function out there behaves the way this one does. And so it just somehow naturally is the one, right? It's the function that we use. It grows a certain way that we like. How fast it grows is just what we wanted. That's about all I can tell you. All right? So.
This is great. Why is it E? What does E stand for?
I think exponential.
Isn't
Yeah.
there some sort of like a golden number?
That's a different type of number that's important, the golden ratio, but it's
Yeah.
not this number.
I had like when I went up to visit my grandmother in Washington, we were getting stuff ready for my grandfather's like
Come on, Lily.
I'm sorry.
No.
Never mind.
You sure?
Yeah.
I'm sure it was a lovely story.
The golden ratio comes from the Fibonacci sequence.
Yeah, everybody knows what that is.
Well, I don't know. Lily was talking about it. Maybe she was trying to get to I thought you were trying to get to the Fibonacci sequence or something.
Yeah, it had something to do with that because I got like little math tattoos, math equations and stuff,
Mhm.
and it had like this thing. I had no idea what it was, so I asked my calculus teacher, and she told me it was the golden ratio.
Yeah.
It was. I had no idea what it was.
Okay. Yeah, that's a different important number. Anytime we have an important number in mathematics, like a really important one, we usually give it a letter to represent. Like pi for 3.14, blah, blah, blah. E is another important one. You're talking about the golden ratio, which comes from the golden spiral, which comes from the Fibonacci sequence. But that is not E. Okay, E is different. All right, what does this look like? What can you tell me just right off the bat what this looks like? It's increasing, right? It's exponential growth. We know it goes through 0, 1. And it goes this way. We know it goes this way because E is 2.718. That's bigger than 1, so we're guaranteed the exponential growth. Yes? The only other way you can actually figure out other points on the graph is to plug it in and make a t-table. So let's make a very quick t-table. This is x, this is e to the x. So you need your calculator for this. We're going to plug in 1, 2, and 3.